KFC's spicy wings, Taco Bell's Nacho fries, and Burger King's Whopper are some of the most iconic fast food items in the world. Each one is built through a precise process of seasoning, layering, and cooking that transforms simple ingredients into crave-worthy meals. In this video, we go inside the kitchens and production lines to uncover exactly how these legendary favorites are made from start to finish. The process begins long before the chicken ever reaches the factory. KFC, like many large-scale food brands, maintains strict supply chain standards for its poultry. Birds are typically sourced from integrated poultry farms that meet the brand's animal welfare, health, and biosecurity requirements. These farms often operate under vertically integrated systems, meaning the entire life cycle of the chicken, from hatchery to grow out to processing, is managed within the same corporate ecosystem. This helps ensure uniformity in bird size, health status, and meat quality, which is critical when producing standardized menu items like spicy wings on an industrial scale. Once the chickens are ready for harvest, they are transported in temperature-controlled, sanitized trucks to centralized poultry processing plants. Here, the live birds go through a humane stunning and slaughtering process, typically involving controlled atmosphere stunning systems. This ensures both ethical handling and meat quality preservation. After slaughter, the birds are defeathered, eviscerated, washed, and cooled, typically through a cold water immersion chilling system that brings the internal temperature of the carcass down to safe levels as quickly as possible. The wings are separated during the portioning phase using high-speed automated cutting equipment. These machines use vision systems to identify and cut at precise anatomical joints, ensuring each wing is uniform in size and shape. This precision is crucial, not just for cooking consistency, but also for proper breeding adhesion and portion control in later steps. The selected wing portions, consisting of the drumette and flat sections, are then transferred to a dedicated wing processing line, where the transformation into spicy wings begins in earnest. Once the wings arrive at the spicy wing processing facility, the first stage involves a thorough inspection. Human inspectors and machine vision systems work in tandem to detect any physical abnormalities or foreign materials. Wings that pass inspection are then routed into a cold, tumbling drum, where they are lightly massaged with a saline-based pre-treatment solution. This helps the meat retain moisture throughout the cooking process and prepares the surface for better batter adhesion. At this stage, some facilities may also inject a phosphate or sodium-based marinade that helps improve juiciness and shelf life, although the exact formulation is proprietary and closely guarded by the brand. Following pre-treatment, the wings move down the line to the breading and seasoning stations, which are often the most visually engaging part of the process. First comes the wet batter application. Wings are submerged into a thin, flour-based slurry that acts as an adhesive layer for the dry coating. This slurry may contain modified starches, leavening agents, and a controlled pH buffer to ensure it sticks properly and reacts correctly during frying. After draining off excess batter, the wings are conveyed into the dry seasoning tumble. This dry breading stage is where the iconic spicy flavor is born. The seasoned flour blend used here is proprietary, but it typically includes a complex mixture of chili powders, paprika, black pepper, garlic powder, onion powder, and other flavoring agents, along with fine-grained flour and cornmeal for texture. A dusting conveyor or tumbling drum ensures even coverage on all sides of the wing. The machinery here is designed to prevent clumping and ensure that only an even, fine layer of breading adheres to each piece. In some facilities, a secondary pass through a flour press or compactor system ensures the breading is firmly embedded into the moist surface, giving it that distinctive crispy crunch once cooked. After seasoning, the wings are briefly set aside for a short dwell time. This resting phase, usually about a minute or two, allows the breading to properly adhere and partially hydrate. Next, they move into the pre-frying section of the line. This stage involves a high-capacity industrial fryer, often filled with high-stability vegetable oils, such as soybean or canola oil. The oil is heated to precisely controlled temperatures, typically around 350 degrees Fahrenheit, and the wings are flash fried for a brief period, just long enough to set the breading and create the initial crispy layer. This pre-frying step is not intended to fully cook the wings, but to lock in the structure of the coating so it maintains its texture during further processing. Once the pre-frying is complete, the wings are immediately conveyed to a blast chilling or par-fry cooling tunnel. This cooling step is critical for preserving the structural integrity of the coating and preventing carryover cooking that could degrade the texture. The temperature is rapidly reduced using forced cold air circulation, typically within a matter of minutes. Once cooled, the wings are either packaged for distribution to KFC outlets where final frying will occur, or they proceed to a fully cooked, frozen format, depending on the specific supply chain model used by the regional franchise. In systems where the wings are fully cooked at the central facility, they enter a final high-temperature fryer that brings the internal temperature of the chicken to over 165 degrees Fahrenheit, ensuring it meets food safety standards. The duration and temperature profile of this final cook are tightly controlled and monitored by programmable logic controllers and sensor arrays that adjust heat levels in real time. The fully cooked wings then exit the fryer onto an inclined conveyor belt fitted with oil removal wipers or air knives to eliminate excess surface oil. Immediately following the cooking phase, the wings are transferred into a spiral or straight line blast freezer, depending on the plant layout. These freezers use ultra-cold air circulated at high velocity to freeze the wings down to storage temperatures of around -18 degrees Celsius. This rapid freezing process, known as individual quick freezing or IQF, prevents the formation of large ice crystals that could damage the structure of the breading and meat. The IQF process ensures that the wings retain their texture, flavor, and moisture when later reheated in KFC kitchens around the world. After freezing, the wings move into the packaging area. Here, automated systems weigh, portion, and package the wings into branded bags or cartons. Each package is checked for weight compliance using dynamic check weighers, and then sealed using high-speed heat sealers or vacuum packaging machines. Every package is labeled with traceability information, including batch codes, production time, and expiration dates, allowing for complete tracking through the supply chain. Quality control is deeply integrated into every step of this process, from metal detectors and X-ray machines that screen for physical contaminants to inline oil filtration systems that continuously purify frying oil to automated sensors that measure moisture content and temperature. Every phase of production is monitored by a combination of human oversight and real-time digital systems. Facilities that produce KFC spicy wings typically operate under globally recognized food safety standards such as HACCP and may also be certified under schemes like BRCGS or SQF. Once the wings are packaged, they enter the cold storage logistics chain. Pallets of frozen wings are loaded into refrigerated trucks that maintain a strict temperature range throughout transportation. These trucks deliver the product to regional distribution centers and eventually to individual KFC restaurants. In some regions, fresh, never frozen versions of the wings are delivered in chilled format and cooked to order in-store. In other areas, particularly where supply chains are longer or temperatures more variable, the IQF model is used to ensure quality is preserved until the point of sale. At the restaurant level, the final stage of the journey unfolds. Frozen or chilled wings are stored in temperature-controlled environments until needed. When ordered, the wings are deep fried one last time in high-capacity fryers, typically operating at around 350 degrees Fahrenheit. This final fry crisps the coating, rehydrates the spices, and brings the product to serving temperature. The result is a spicy, crispy, juicy wing that delivers the iconic KFC experience customers have come to expect. The process begins with the raw foundation of the product, the humble potato, but not just any potato will do. The ideal potato for Taco Bell nacho fries is typically a variety high in dry matter content, often russet Burbank or Shepherdy types, known for their low moisture, high starch, and robust structure. These characteristics ensure the fries achieve the perfect balance between a fluffy interior and crispy exterior after frying. These potatoes are sourced from large, vertically integrated farms primarily located in the Pacific Northwest of the United States or similar potato-producing regions around the world, where the climate and soil are optimal for consistent, large-scale yields. Harvesting is done using advanced mechanical harvesters that dig up the potatoes and gently lift them onto conveyor systems to avoid bruising. From there, they are transported to centralized washing and grading facilities where they are sorted by size, inspected for blemishes or defects, and washed thoroughly using high-pressure water jets and rotating brushes. Any potatoes that do not meet the factory standards are diverted to other uses such as dehydrated flakes or animal feed. Once approved, the potatoes are delivered in bulk to industrial fry manufacturing plants where the transformation into nacho fries begins. At this stage, they are held in temperature and humidity-controlled storage rooms to preserve their starch content and prevent premature sprouting. When it's time to process, the potatoes are first sent through a series of peelers, usually steam peelers or abrasive roller systems, that efficiently remove the skins while minimizing product loss. This step is closely monitored using yield tracking sensors to ensure peeling efficiency and minimize waste. The peeled potatoes are then sliced using high-speed industrial cutting machines fitted with grid blades that create uniform fry shapes, typically thicker than traditional fast food fries to support the added seasoning and prevent oversaturation. These slicing systems are calibrated down to the millimeter to ensure each fry is cut to precise specifications, generally around 1 4-inch to 3 8-inch thickness. High-pressure water flumes carry the sliced fries through the line at speeds exceeding 20 feet per second, ensuring rapid, continuous processing. Next comes the blanching stage, where the sliced fries are briefly immersed in hot water, typically around 170 to 180 degrees Fahrenheit, for a few minutes. This partial cooking phase serves multiple purposes. It removes excess surface sugars that could cause uneven browning during frying, activates enzymes that improve texture, and begins the gelatinization of internal starches. After blanching, the fries are quickly cooled using chilled water or air blast tunnels to stop the cooking process and firm up the structure. Now partially cooked, the fries enter the par frying line. This is their first encounter with oil, and it's where the initial crispy layer begins to form. Large industrial fryers filled with high stability oil, such as a blend of sunflower and canola oils, are heated to around 350 degrees Fahrenheit. The fries are submerged for a precise amount of time, usually less than 90 seconds, just long enough to form a protective crust on the outside. Sensors and computerized fry time controllers ensure that oil temperature remains consistent to prevent flavor degradation or uneven cooking. Immediately after par frying, the fries pass through a de-oiling conveyor, where vibrating belts and air knives remove excess surface oil. The fries are then conveyed into a seasoning chamber, which is one of the most distinctive stages in the production process. Here, Taco Bell's proprietary spice blend is applied. The exact recipe is tightly controlled, but it's known to include ingredients like paprika, garlic powder, onion powder, chili powder, and finely milled salt, combined with natural flavor enhancers and color stabilizers. A continuous tumbling drum with angled paddles ensures every fry is evenly coated, while fine misting sprays may be used to lightly dampen the fries and help the powder adhere without making the product soggy. Once seasoned, the fries are flash frozen using a high-velocity IQF freezer system. In this stage, powerful cold air, chilled to minus 40 degrees Fahrenheit or below, is blasted across the fries in a spiral or linear tunnel. This rapid freezing process locks in flavor, moisture, and structure, preventing ice crystals from damaging the surface coating. The IQF method ensures that each fry remains separate and doesn't clump, which is critical for later portioning in restaurant operations. After freezing, the fries are transferred to the packaging line. Automated systems weigh and fill bulk fry containers or food service size bags, which are then sealed using heat sealing equipment. Each bag is printed with a batch code, production date, and temperature tracking markers. Metal detectors and X-ray machines scan each package to ensure no foreign materials are present, a key component of food safety compliance. Packaged fries are loaded onto pallets and stored in deep freeze warehouses until they are ready for distribution. The Nacho cheese sauce, an essential companion to the fries, has its own equally rigorous production process. The base of the sauce is typically a processed cheese blend made from cheddar, milk proteins, and emulsifying salts like sodium citrate or sodium phosphate. These ingredients are carefully combined in industrial kettles equipped with steam-jacketed heating systems and high-shear mixing paddles. Stabilizers, such as modified starches and gums, may be added to ensure the sauce maintains a smooth, pourable texture even after cooling and reheating. Once the cheese base is prepared, spices are added, typically a blend of jalapeno flavoring, chili extract, and other proprietary ingredients that give the nacho sauce its signature kick. The mixture is emulsified under vacuum to remove air bubbles and then pasteurized using a continuous flow heat exchanger. This process heats the sauce to over 165 degrees Fahrenheit for a controlled amount of time to destroy microbial contaminants while preserving flavor and color. After pasteurization, the cheese sauce is hot-filled into sterilized pouches or cups under aseptic conditions. These containers are then sealed and either cooled through a water cascade system or sent into spiral chillers. The sealed containers are packed into cartons and labeled for refrigerated or shelf-stable distribution, depending on the formulation used for the region's supply chain. With both the fries and the cheese sauce packaged and preserved, the products are transported through a cold chain logistics network. Fries are shipped frozen in insulated trucks to regional distribution centers and then delivered to Taco Bell restaurants in freezer-safe cartons. The cheese sauce, often refrigerated, follows a separate cold storage route. Each location has specific temperature monitoring systems in place to ensure food safety compliance throughout transit and storage. At the restaurant level, the frozen fries are stored in walk-in freezers until needed. When an order comes in, the fries are portioned out and deep fried in vegetable oil, using high-efficiency commercial fryers. This final fry is where the crispy golden texture is fully developed. The temperature is maintained at a consistent 350 degrees Fahrenheit, and the fry time is usually between 2 and 3 minutes. Once cooked, the fries are immediately drained, then served hot in Taco Bell branded packaging. The cheese sauce is reheated either in a hot holding unit or using a hot water bath system that brings it to serving temperature without burning. The sauce must reach at least 140 degrees Fahrenheit to meet food safety and quality requirements. Once heated, the sauce is portioned into small dipping containers or drizzled directly over the fries in some menu variants. Throughout the entire industrial journey of nacho fries, rigorous quality assurance and food safety protocols are in place. Samples from each batch are taken at various stages and tested for microbiological contaminants, seasoning distribution, oil content, moisture levels, and cooking performance. Facilities operate under strict guidelines such as FDA, FSMA requirements or international standards like ISO 22000 and HACCP. Every element of production, from the slicing of potatoes to the pasteurization of cheese sauce, is documented and auditable to ensure full traceability. The process begins with the heart of the Whopper, the beef patty. Burger King has long differentiated its burgers by using a flame-grilled method, but before the grill comes into play, the patty must first be produced. Beef is sourced from large-scale, certified suppliers that adhere to strict animal welfare, traceability, and sustainability standards. These suppliers operate integrated meat processing facilities where cattle are harvested and broken down into primal and subprimal cuts under USDA or equivalent oversight. The beef used for Whoppers is typically derived from a mix of chuck, round, and sirloin cuts, blended to achieve a desired fat content, often around 20%, for optimal juiciness and grill performance. Once the meat is ground, it is passed through an emulsifying system that ensures even distribution of fat and protein. This step helps prevent gristle pockets and improves the patty's binding structure. The ground beef mixture is then conveyed to high-speed patty-forming machines that press and extrude the meat into uniform rounds using a die plate and compression mold. These industrial formers operate at speeds of hundreds of patties per minute and are capable of adjusting thickness and diameter to exact specifications, typically around a quarter-pound raw weight for each Whopper patty. The formed patties are placed on a conveyor belt and flash frozen using cryogenic tunnel freezers or spiral IQF systems that use liquid nitrogen or carbon dioxide to rapidly bring the internal temperature below -18 degrees Celsius. This ensures that each patty retains its cellular structure and juiciness upon cooking. Once frozen, the patties are transferred to automated packaging lines, where they are stacked in moisture barrier cartons or vacuum-sealed pouches, labeled with production dates, and passed through metal detectors before being palletized for frozen storage and global distribution. Equally important to the Whopper is the bun, a sesame seed-topped, split bread roll that undergoes its own industrial journey. Buns are produced at high-capacity commercial bakeries where production lines can generate tens of thousands of units per hour. The dough is made from a blend of wheat flour, water, sugar, yeast, and vegetable oil, along with dough conditioners and preservatives to maintain softness and shelf life. The mixing phase involves large-scale planetary or spiral mixers that knead the dough to the correct gluten development. After mixing, the dough enters a resting phase in fermentation-proofing chambers where it rises under controlled temperature and humidity. The dough is then portioned by volumetric dividers and shaped into balls by automated rounders. These pre-shaped dough pieces are loaded onto proofing trays and undergo a final rise before baking. The tops are lightly misted with water or egg wash and sprinkled with white sesame seeds by mechanical applicators. The buns are baked in continuous tunnel ovens that stretch over 100 feet in length and operate at temperatures exceeding 400 degrees Fahrenheit. Once baked, they pass through a rapid cooling system using ambient or chilled forced air to bring their temperature down before slicing. Each bun is sliced horizontally by high-speed rotary blades and inspected for consistency. To maintain freshness, buns are either packaged in modified atmosphere packaging or frozen shortly after cooling and then bagged in polyethylene liners. They are coated with traceability information and packed into corrugated cartons for delivery to regional warehouses and restaurants. The vegetables, lettuce, tomatoes, and onions are sourced from contracted agricultural operations that follow strict GAP protocols. Iceberg lettuce, preferred for its crunch, is harvested using semi-automated field machines that cut and core the heads in one motion. The lettuce is then transported in refrigerated trucks to processing facilities where it is washed in sanitized flumes, dried using centrifugal systems, and shredded using stainless steel cutting blades designed to preserve crispness without bruising the leaves. Tomatoes are selected for firmness and uniform diameter to ensure neat slices. They are cleaned using high-pressure spray washers and sliced using rotary slicers fitted with adjustable blades. The sliced tomatoes are layered into stackable trays or nested compartments to prevent crushing during transit. Similarly, onions are peeled mechanically using high-pressure air systems, sliced into rings, and packaged under chilled conditions to retain freshness. The pickles, another key flavor component, are made from cucumbers processed in bulk brining tanks. After harvest, cucumbers are washed, sorted by size, and submerged in a vinegar-based brine seasoned with salt and spices. After fermentation or quick pickling, depending on the formulation, they are sliced into consistent chips using high-speed slicers and packaged in oxygen barrier pouches or buckets for food service use. Condiments for the Whopper, primarily mayonnaise and ketchup, are manufactured in specialized condiment production facilities. Mayonnaise production begins with the emulsification of oil, egg yolk, vinegar, and stabilizers in high-shear mixing tanks equipped with homogenizers. The emulsion is pasteurized through a plate heat exchanger to eliminate pathogens while preserving viscosity and color. Ketchup is cooked in steam-jacketed kettles and blended with tomato concentrate, sugar, vinegar, and a proprietary spice mix. Both condiments are filled into sterile plastic pouches, bag-in-box systems, or pump-compatible canisters for use in restaurant dispensers. Cheese slices used in variants like the Whopper with cheese are produced from processed cheese blends that ensure meltability and consistency. These are extruded into sheets, cut into slices, and layered with separators to prevent sticking. The slices are then vacuum packed or nitrogen flushed for refrigerated storage and distribution. With all components produced and shipped to Burger King locations, the final assembly of the Whopper occurs in the restaurant, but the process is built upon a strict operational framework. Each location stores the beef patties in a walk-in freezer and thaws them under refrigerated conditions. When an order is placed, the patty is cooked on Burger King's signature broiler, a chain-driven flame grill system that uses open gas flames to charbroil the beef as it passes through on a conveyor. This broiler, unique to Burger King, is a marvel of fast food engineering. The system allows for consistent flame contact, resulting in seared grill marks and a characteristic smoky flavor. Sensors monitor patty temperature and broiler speed to ensure the patty is fully cooked to a safe internal temperature of 160 degrees Fahrenheit without overcooking. The cooked patties are briefly held in warming trays under precise time constraints to maintain texture and temperature. Meanwhile, the buns are toasted in a dedicated bun toaster, which uses radiant heat or infrared technology to give the interior a light crispness while leaving the exterior soft. The assembly station is laid out for ergonomic speed and accuracy. A Whopper bun base is placed on a wrapping sheet or clamshell box. The bottom bun receives a layer of mayonnaise, followed by shredded lettuce, 2 to 3 tomato slices, and the flame-grilled patty. Next come the ketchup, sliced onions, pickle chips, and finally the top bun. Employees are trained to follow a specific build order and ingredient placement protocol to maintain consistency across all locations. Once assembled, the Whopper is either wrapped or boxed using pre-printed branded materials and placed into warming cabinets for immediate delivery to the customer or drive-through window. Food safety, quality assurance, and traceability are enforced at every step of the Whopper's life cycle. Raw materials are tracked via digital systems that log harvest dates, batch codes, and production facilities. Burger King suppliers and franchises are subject to regular third-party audits, temperature verification, and microbiological sampling. Any deviation from standard operating procedures, whether it be in patty cook temperature, bun freshness, or condiment integrity, triggers corrective action protocols. Chocolate begins its life not in the factory, but on the tropical cacao farms that that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate-making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120–140 degrees Celsius. The final stage of roasting is known as development or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, the nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, the chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks. But every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The industrial production of condensed milk begins with the careful reception and preparation of raw cow's milk, a phase that determines the quality, efficiency, and final yield of the entire operation. As raw milk arrives at the condensed milk manufacturing facility, typically transported in insulated stainless steel tankers from contracted dairy farms, the first priority is immediate and rigorous quality assessment. Each truckload contains tens of thousands of liters of milk, and every batch must be verified to meet precise industrial standards before being accepted into the plant's supply chain. This initial phase involves a set of standardized protocols carried out in a dedicated receiving bay, equipped with specialized sampling and testing equipment. Upon arrival, the truck is docked to an unloading station, where automated lines connect directly to the tanker's valve. Before unloading can commence, operators perform a series of tests on a representative sample extracted from the tanker. This is done using a sanitized dipper or through a sample port using aseptic techniques to avoid contamination. The sample is then transferred to the plant's on-site quality control lab. Inside this lab, technicians first conduct a sensory inspection, evaluating the milk's color, smell, and presence of any visible particulates. While this step is basic, it's essential in immediately identifying any batches with gross spoilage or foreign contamination. The next series of tests are chemical and microbiological. A cryoscope is used to determine the freezing point of the milk, which helps identify dilution with water. Industrial condensed milk relies on unadulterated raw milk with tightly controlled fat and solids not fat contents. Any dilution affects the solids concentration required for the evaporation phase later on. Following this, infrared spectroscopy or mid-infrared analyzers are used to determine precise fat, protein, and lactose levels. These readings are compared against production targets, usually 3.5 to 4.0% fat and 8.5 to 9.0% SNF. If any component falls out of range, the milk may be either rejected or diverted to other dairy product lines. Another critical check is for microbial load. A rapid plate count or ATP bioluminescence test evaluates the total bacterial count per milliliter. Condensed milk production cannot start with high bacterial loads, as the concentration process would also concentrate any microbial byproducts, leading to off flavors and safety risks. Acceptable raw milk generally must have fewer than 100,000 colony-forming units per ml, with many plants enforcing even tighter limits. Additionally, presence of pathogens such as Listeria or Salmonella are monitored using immunoassay kits or PCR-based rapid tests. Antibiotic residue testing is also performed using either SNAP tests or microbial inhibition assays, since antibiotic contamination can disrupt the fermentation steps used in other dairy operations and might violate export regulations. If the sample passes all tests, the milk is cleared for unloading. The truck's contents are then pumped via sanitary stainless steel pipelines into raw milk holding tanks located within a temperature-controlled section of the facility. These tanks, typically ranging from 20,000 to 50,000 liters in capacity, are jacketed and agitated to maintain a constant temperature of around 4 degrees Celsius. At this stage, the milk is still unpasteurized and considered perishable, so time and temperature control are critical. The tanks are equipped with inline thermometers and CIP spray balls that will sanitize the internal surfaces between batches to prevent cross-contamination. The next step in the process is milk clarification and standardization. This is a pivotal moment where physical impurities and excess variability in composition are removed. The raw milk is fed from the storage tanks to a centrifugal clarifier, a high-speed rotating bowl separator that uses the density differences between milk solids and liquid to remove somatic cells, dirt, and other non-milk particles. The milk enters the spinning drum through a feed pipe, and under centrifugal force, heavier particles are flung outward against the bowl walls and discharged intermittently via sludge ejection ports. After clarification, the milk is sent to a cream separator. This piece of equipment operates similarly to the clarifier, but focuses on removing and isolating the cream layer from the skim milk portion. Depending on the desired end product specifications, some or all of the separated cream may be blended back in. This is where the standardization process comes into play. Condensed milk requires a tightly defined balance between fat content and total milk solids. Operators adjust this balance using inline blending systems, automated control loops equipped with flow meters and density sensors. The goal is to create a uniform milk base, typically around 8.5% fat and 22% total solids before it proceeds to pasteurization and evaporation. Any deviation at this stage would affect the efficiency of the next stages and could compromise the desired thickness, sweetness, and shelf life of the condensed milk. In more advanced factories, these composition adjustments are performed entirely by automated PLC systems. These use real-time data collected from inline sensors to control proportioning valves and regulate the mixing of cream and skim milk streams without any manual input. This level of automation not only ensures consistency, but reduces waste and energy use. The standardized milk is now homogeneous in composition, free of debris, and ready for thermal treatment. Before entering the pasteurizer, it may pass through a deaerator, a vacuum chamber that removes entrapped gases such as oxygen and carbon dioxide, which, if left in, could promote oxidation of fats and off flavors during storage. But up next is a step that changes the physical properties of the milk at a fundamental level. With the raw milk now cleaned, standardized, and compositionally balanced, it's time for it to undergo pasteurization and heat treatment, a step that prepares it for concentration without microbial risk or protein denaturation. This phase involves an intricate dance between temperature, pressure, and time, and it sets the stage for the transformative evaporation process that gives condensed milk its name. Now that the raw milk has been thoroughly received, clarified, and compositionally standardized, it is ready for thermal treatment. The next phase in the factory process is pasteurization, which is critical in destroying any pathogenic or spoilage microorganisms present in the milk. Pasteurization must be done with precise timing and temperature control to ensure microbial inactivation without damaging the milk's nutritional or functional properties, especially since this milk will soon undergo evaporation, which puts it under further thermal stress. To carry this out, the milk is directed from the holding tanks into a continuous flow, high-temperature, short-time pasteurization unit, which is the standard in industrial dairy processing. The HTST system typically consists of a series of plate heat exchangers that are engineered to raise the milk temperature to approximately 85 degrees Celsius for 15 to 20 seconds. This is hotter and slightly longer than conventional drinking milk pasteurization, as condensed milk requires greater microbial stability due to its extended shelf life. The process begins in the regeneration section of the plate heat exchanger, where incoming cold raw milk is preheated by outgoing pasteurized milk, allowing energy recovery and efficiency gains of up to 90%. The milk then moves through the heating section, where it is brought to the target temperature using hot water or steam circulated on the opposite side of the stainless steel plates. The timing of exposure is controlled by the flow rate and volume of the holding tubes, ensuring that every particle of milk receives uniform treatment. After pasteurization, the milk passes into a holding cell monitored by thermocouples and flow diversion valves. If the milk fails to reach or maintain the required pasteurization conditions, it is automatically diverted back to the raw milk tank for reprocessing. Once verified, the pasteurized milk is cooled again in the regeneration section, where it gives off its heat to the incoming raw milk, and then further chilled to around 60 degrees Celsius in preparation for the next crucial step, evaporation. Before entering the evaporator, the milk passes through a balance tank that helps maintain a constant feed rate into the evaporation system, stabilizing flow and avoiding temperature fluctuations that could cause burn-on or fouling inside the evaporator tubes. Now it's time to go into the evaporation stage, which is arguably the heart of the condensed milk production process. This is where the milk is physically transformed, thickened into a rich, viscous product through the removal of water. The goal here is to reduce the water content from its original 87% down to around 60%, achieving a final concentration of about 28% milk solids and 44% added sugar in the case of sweetened condensed milk. This is achieved through multi-effect vacuum evaporation, an energy-efficient process that allows for large-scale water removal without subjecting the milk to damaging high temperatures. The milk enters a multiple effect falling film evaporator, which is the industry standard for large volume dairy processing. In this system, the pasteurized milk is introduced at the top of vertical stainless steel tubes where it forms a thin film as it flows downward. Simultaneously, steam is injected into adjacent chambers that surround the tubes, heating them indirectly. Because the evaporator is operated under vacuum, often at pressures around 70 to 100 millibar, the boiling point of the milk is reduced to around 55 degrees Celsius. This protects the sensitive proteins, sugars, and fats from heat-induced damage, preserving both flavor and nutritional quality. In a multi-effect setup, the vapor produced from one stage is used to heat the next stage, drastically improving energy efficiency. A typical 5-effect evaporator can remove over 85% of the water from milk with minimal energy input, thanks to this cascading reuse of thermal energy. The evaporated water is condensed and collected as waste heat condensate, which can later be recycled within the plant for cleaning processes or steam generation. Inside the evaporator, the thin film of milk continuously loses moisture as it falls. The combination of short residence time, low boiling point, and efficient heat transfer ensures that concentration occurs evenly and rapidly. By the time the milk reaches the bottom of the final effect, it has reached a viscous, concentrated state with a solid content of around 45%. At this point, it is discharged into an intermediate concentrate tank, where it is gently agitated and kept warm to prevent crystallization or skin formation on the surface. But the evaporation process alone does not fully define condensed milk as we know it, especially in the case of sweetened condensed milk. Once the desired solids concentration is achieved, the next critical step is the addition of sugar, which is not merely for taste, but serves as a functional preservative. The high sugar content lowers the water activity of the product to a point where microbial growth is virtually halted, granting it a long shelf life without refrigeration. The method of sugar addition must be extremely precise, as the wrong concentration can lead to issues like crystallization, viscosity problems, or even fermentation in rare cases. To do this, refined white sugar, typically sucrose, is added to the concentrated milk in the form of a hot sugar syrup. This syrup is prepared separately in jacketed mixing vessels, where dry granulated sugar is dissolved in water and heated to around 70 degrees Celsius. The syrup is filtered to remove any particulate matter and pumped into the concentrate tank under controlled flow rates. The typical formulation is around 46% sucrose by weight in the final product, which is determined by a combination of inline refractometers and density meters. The mixing of sugar syrup into the concentrate must be uniform to prevent localized crystallization and is often aided by low shear agitators that maintain homogeneity without introducing air. As the sugar is added, the milk becomes even more viscous and dense. At this point, the product's temperature is carefully maintained between 60 degrees Celsius and 65 degrees Celsius, as dropping below this range can initiate premature crystallization, while higher temperatures can scorch the milk solids. Once the sugar is fully integrated, the mixture is briefly held in a jacketed holding tank for a process known as equilibration, which allows any remaining air bubbles to rise and dissipate and gives time for the solution to reach equilibrium in terms of water activity and solute concentration. This marks the end of the thermal and compositional transformation stages. From a microbiological and physicochemical standpoint, the product is now shelf-stable, viscous, and chemically preserved by both heat treatment and high sugar concentration. However, it's not yet ready for packaging. There are still important steps to take involving cooling, crystallization control, and downstream finishing that are vital to achieving the smooth texture and glossy appearance that define high-quality condensed milk. With the concentrated sweetened milk now fully blended and equilibrated, the next critical phase in the condensed milk manufacturing process is controlled cooling and crystallization. This step is vital not only to achieving the desired texture and viscosity, but also to ensuring long-term product stability. If cooling is done too quickly or without proper control over nucleation, the lactose and sucrose in the product can crystallize into large, gritty particles. This not only affects mouthfeel, but can also lead to phase separation over time. To avoid this, the condensed milk is sent through a carefully engineered cooling and seeding system that promotes the formation of microcrystals, small, evenly distributed sugar crystals that give condensed milk its signature, smooth, glossy consistency. The cooling system typically consists of scraped surface heat exchangers or jacketed tubular coolers. These systems are designed to handle highly viscous liquids and provide a high degree of thermal control. In scraped surface heat exchangers, the condensed milk flows through a cylindrical barrel while rotating blades constantly scrape the inner surface. This ensures that no product burns or sticks to the hot surface, and that the entire volume of milk is uniformly cooled. The cooling medium, usually chilled glycol or water, is circulated through the jacket, gradually lowering the milk temperature from around 65 degrees Celsius to 30-35 degrees Celsius. As the milk cools, it passes through a crystallization chamber where it is inoculated with fine lactose or sucrose seed crystals. These seed crystals are introduced in a controlled manner using a dosing system that meters out microscopic crystals with a high surface area. The goal is to initiate crystallization at a molecular level, encouraging the dissolved sugars to form consistent and extremely fine crystals rather than large, coarse ones. Agitators in the crystallization chamber are designed to promote gentle but thorough mixing, ensuring uniform distribution of the seed material without incorporating excess air, which could lead to oxidation or microbial contamination. Once seeded, the mixture is held at a stable crystallization temperature, typically around 30 degrees Celsius, for a period ranging from 30 to 90 minutes, depending on the batch size and product formulation. This resting period allows the crystals to grow slightly while remaining small and suspended, forming a delicate lattice within the viscous matrix of the milk. It is during this stage that the final texture of the condensed milk is locked in. Operators closely monitor the product's Brix value, viscosity, and temperature, using inline sensors and laboratory sampling to ensure that the crystallization proceeds according to specification. After the crystallization phase, the product enters the deaeration stage. Despite all precautions taken during processing, the condensed milk will inevitably contain some entrapped air, either from mechanical mixing, seeding, or agitation. This air must be removed before packaging to prevent oxidation, which can degrade both flavor and color over time. Deaeration also helps improve fill accuracy during packaging, ensuring a stable and uniform product weight in each container. Deaeration is typically carried out in a vacuum deaerator tank. The condensed milk is pumped into the tank, which is maintained under a vacuum of around -0.8 bars. Inside the tank, the milk is spread into a thin film across a series of rotating trays or falling film surfaces, maximizing the exposed surface area. As the product spreads out under vacuum, dissolved gases and trapped air are released and drawn out by the vacuum pump system. In some systems, nitrogen gas is also bubbled through the product as a stripping agent to help displace oxygen more effectively. This process is continuously monitored with oxygen sensors to ensure minimal residual oxygen levels in the final product, typically less than 0.5 milligrams per liter. Once deaerated, the condensed milk is often passed through a final homogenization stage. While not strictly required in all formulations, homogenization is frequently used to improve product consistency, prevent fat separation, and extend shelf stability. In this process, the milk is forced through a narrow orifice under high pressure, usually between 100 to 150 bar, causing the fat globules to break down into much smaller sizes, typically less than 1 micron in diameter. This prevents creaming or separation during storage and gives the final product a more uniform mouthfeel. The homogenizer used in this step is typically a two-stage piston-type homogenizer. In the first stage, pressure is applied to break apart the fat globules. In the second stage, the product is passed through an impact ring to further disperse and stabilize the emulsion. This ensures that the fat remains evenly distributed throughout the viscous condensed milk matrix, even after months of storage on a shelf. The process must be carefully balanced to avoid over-shearing the product, which could break the sugar crystal structure and lead to syneresis or texture issues. With the product now fully processed, it moves to the packaging line. Before any milk enters a can or a tube, the packaging material itself must undergo preparation. Metal cans are the most common format for condensed milk, though plastic tubes and laminated pouches are also used depending on market demands. The cans arrive at the factory either as pre-formed containers or as rolled flat blanks that are formed and sealed on site using can-forming machinery. If using pre-formed cans, the first step is depalletizing and feeding. The cans are automatically unloaded from shipping pallets and fed into a cleaning system via conveyor belts. Here, they pass through a high-pressure air blower system that removes dust and debris. They may also pass through an inverted rinse tunnel that sprays them with sterile water or a mild sanitizing solution. Optical sensors verify that each can is intact and free of damage before it proceeds. The clean cans are then transported to the filling station, where they are indexed into position beneath nozzles connected to a positive displacement filler system. These filling machines are designed to handle thick, viscous liquids with high precision. A typical condensed milk filling machine includes a volumetric dosing mechanism that ensures every can receives the exact same quantity, usually around 397 grams, the standard retail size. Sensors ensure the nozzles do not drip or splash, and the filling process is conducted in a low oxygen environment to prevent post-process contamination. As cans are filled, they immediately move to the vacuum closing station. This is another critical step in ensuring product longevity. Before the lid is sealed, a vacuum is applied to the headspace in the can to remove residual air. This helps prevent oxidation and maintains the slight negative pressure required for a tight seal. The lid is then applied and hermetically sealed using a double seam seaming machine. This creates an airtight seal by mechanically folding and compressing the lid and can flange together in 2 operations. The quality of this seal is checked automatically using seam gauges and vision inspection systems to detect any defects or incomplete closures. After sealing, the cans enter a hot water bath or steam chamber for thermal holding. This step, known as in-can sterilization or thermal stabilization, involves heating the sealed cans to around 85 to 90 degrees Celsius for 15 to 20 minutes. This serves several functions. It neutralizes any residual microbes that may have entered during filling, helps equalize pressure inside the can, and further reduces the water activity of the product. The heating process is tightly controlled using a time temperature data logger to ensure consistency across batches. Once the thermal holding is complete, the cans are rapidly cooled using chilled water sprays or immersion tunnels. This quick cooling halts the cooking process and helps set the product structure inside the can. It also prevents over-darkening, which can occur due to Maillard reactions between milk proteins and sugars at elevated temperatures. The cans are then dried using air knives and conveyed to the labeling and coding area. Each can is now labeled with full product information, including nutritional facts, production batch codes, expiration dates, and allergen warnings. Laser coders or inkjet printers apply traceability codes directly onto the lid or bottom of each can, allowing for full tracking throughout the supply chain. These codes are critical for food safety as they allow for rapid recall or identification of affected batches in the rare event of a contamination issue. From here, the cans are packed into cartons or shrink-wrapped into bundles using automated case packers. The cartons are stacked onto pallets and wrapped with stretch film for transport. At this stage, finished condensed milk is subjected to final quality inspection, where random samples from each batch are tested for Brix value, fat content, microbial load, viscosity, and packaging integrity. Once the batch is cleared, it is released for distribution. With the cans now fully sealed, labeled, and palletized, the condensed milk moves into the final stretch of its industrial journey: post-production storage, distribution, and market readiness. While it may seem that the heavy lifting is over, these concluding steps are far more complex and technologically managed than they first appear. Factories invest significant resources to ensure that every can of condensed milk not only leaves the facility in perfect condition, but also maintains its quality throughout the entire shelf life, often up to 2 years or more. Immediately after packaging, pallets of condensed milk are transferred to temperature-controlled finished goods warehouses. The climate in these storage areas is tightly regulated, typically kept between 15 degrees Celsius and 25 degrees Celsius, with relative humidity under 60%. This environment prevents moisture accumulation on the can surfaces and limits the rate of any chemical reactions inside the product, such as non-enzymatic browning. Even though the condensed milk is shelf-stable, excessive heat over time can darken the color and subtly change the flavor profile. These storage conditions are monitored 24/7 using IoT-connected environmental sensors that send real-time data to the facility's central control system. Each pallet is barcoded with batch numbers and entered into a digital warehouse management system. This system not only tracks location and inventory levels, but also enforces FIFO protocols to ensure older batches are distributed before newer ones. The traceability codes printed earlier on the cans come into play again here. Every single unit can be traced back to its raw milk intake, processing parameters, operator ID, and time-stamped process logs. This full chain traceability is a critical part of modern food safety compliance. When orders are received from retailers, exporters, or institutional buyers, automated robotic pallet pickers retrieve the relevant stock and move it to the outbound shipping area. Here, it is loaded into refrigerated or insulated trucks, depending on the destination and regional climatic conditions. In many cases, international shipments involve placing pallets into reefer containers that maintain stable temperatures for transoceanic shipping routes. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3-ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes, varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analysed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of Ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact.